Well, grade 11s, we're on our fourth day of sinusoidal functions, and so far we haven't had any videos. So we've had a little break from that, and I'm thinking maybe it's just as well I'm here alone tonight and not in front of you, since I am reintroducing transformations of functions, and we're applying that to sinusoidal functions. Nobody can throw anything at me at the moment. So here we go. Y equals sine x. What do we know? You know what it graphs like. You were working on that the last few days, and you know the key to remembering sine x is that the sine of 0 is 0, so your starting place is at 0, 0. It goes up, back, down, back up within 360 degrees. So there's things that we need to be able to label for a sine graph. The period of our parent function y equals sine x is 360 degrees. That is the time or the domain that it takes to do one cycle. The maximum value is 1. The minimum value is -1. So you know that your range then is from -1 to 1 and all the bits in between. The domain, x can be any real number forever and ever in both directions. You know that you have a number of x-intercepts, the first one being 0, 0, 180, 0, 360, 0, and so on. So, isn't this Christmassy? For our x-intercepts, we have 0, we have plus and minus 180, we have plus or minus 360, and so on. Adding 180 each time, we could find all of our x-intercepts, and there's one y-intercept, and that is 0. Y equals cos x. We also spent time with that, and they're awfully similar. But the initial value, or the y-intercept, is at 1. So we start on the maximum value and travel through the minimum back to a maximum. Many things are the same. The period is 360. It takes 360 degrees to complete one cycle. The range. Maximum and minimum values are the same. Y lies between -1 and 1, and it is a continuous function. X-intercepts are a little different, however. We have x-intercepts at 90, 270, and so on. X-intercepts at plus and minus 90, plus and minus 270, and we continue by adding 180 each time, and we'll get our x-intercepts. Y-intercept for this one is 1. And that's the handy point to remember for cos. But, and you've seen this already, with our sine and our cos curves, we often apply these things in science, and so we have some new lingo. So this applies to both sine and cos. The transformations look just like they did before. And the old language that we would use, if we throw a number at the front of the function, that will be a vertical change. And if it is a negative, if a is negative, there will be a reflection across the x-axis the same. But in our new language, this would be the amplitude. So if a is a large number, you have a large amplitude. If a is a fraction, you have a vertical compression, so you would have a very small amplitude, less than 1. B is a horizontal stretch or compression, and we can still think of it in those terms, but your horizontal stretch or compression is going to change the period, or how long it takes to do one full cycle. Horizontal translation, some books refer to that as a phase shift. So that's the number that we add in the brackets. And don't forget that things are backwards when they're horizontal. The C is a vertical translation. up or down, and it is as you think, positive is up, we will call that a displacement. So make note of the new lingo because the word problems will all refer to that and you need to know what kind of a transformation that involves. So let's look at a couple of equations. The first one, y equals 3 to x minus 60 degrees plus 4. So the first number, and I always work left to right, the first number is the 3. So that is a vertical, so in brackets, because that's our old language, vertical translation, vertical expansion, or stretch, factor 3. That will make our amplitude 3 instead of 1. The period has changed. This number is going to change the period. So in our old language, we would say that was a horizontal compression, factor 1/2. So the period changes, and it's not 360 anymore. It will be 360 divided by 2, which is 180. And that makes sense to be a compression. It now takes less distance to make the same cycle in 180 degrees instead of 360. So we always take the period, is 360 divided by that number. The next two, the 60 degrees. It's a horizontal translation, 60 right, and we will call that a phase shift, 60 right. And last is plus 4, vertical translation, up 4. This is a displacement, and we would often say vertical displacement. That word is whatever. Displacement is 4. Y equals minus 2 cos 3x plus 30 plus 3. Working from left to right, my negative. It is upside down. The amplitude is 2. That 3 is going to change the period. So the period will be 360 normally, divided by 3 gives us our new period, 120. The x plus 30 is a horizontal translation left 30 degrees. It is a phase shift. $30 left. And lastly, our displacement is 3 upwards. So not so bad, we just have to remember the language. This one, I should have hidden that second from you, but this is the function that we're given. Y equals 4 cos a half x plus 90. But don't forget, when we want to know correctly, this might be hard to tell, how far left we are traveling, it is better to have it written as x plus a number or x minus a number, not with a coefficient. So I factored this coefficient out. And now it is very clear what transformations have happened. So left to right, our amplitude is 4. Our function has been vertically stretched, factor 4. Second thing that I see is the half. That is a horizontal expansion, factor 2. The period has been adjusted, 360 divided by a half. And although that is ugly, that gives us a period of 720. X plus 100 is a phase shift. shift left 180. And lastly, displacement down 1. Let's do a word problem. The water depth in a harbor is 21 meters at high tide and 11 meters at low tide. One cycle is completed every 12 hours. Find, I've cut the word off here, find an equation for the water depth as a function of time, t hours after low tide. I think, you know me, I think a sketch is worth a lot. So just a really rough sketch. We have height as a function of time. So time is independent, and it is in hours. We have one water depth, so let's call it depth in meters. I just want to make sure I've got all my units. Yes, I do. And it says we're going to find this function after low tide. So we're going to start at low tide, go to high tide, back to low tide again. So our low tide is 11 meters. And we're going to start after low tide. So 11. See how rough it is? But it's just going to give me a sense of what's going on. So we're going to start at 11. Going to go to high tide and back again. Why can we say that the depth of water from high tide to low tide would be a periodic function? We want to come up with an equation for this. Oh, I can put this number on as well. It takes 12 hours to go from low tide to high tide to low tide again, which again makes sense. We want an equation. We know roughly what that equation is going to look like. I know that I'm going to want the period and the amplitude and any shifts and displacement. So let's brainstorm for a bit here. Period, amplitude, phase shift. And we can talk about it with our old lingo too, displacement. The displacement, sorry, the period is easy. It takes 12 hours. In my equation, I'm going to need to write a number. I want to check what letter we used. B. We need a letter B, a number B, a number for the letter B, where if I do 360 divided by that letter, I get 12. Because my period, I always find it by 360 divided by that horizontal stretch. And I will get the period. And I know what the period is. So I can find B. The amplitude, well, that's a little trickier. The amplitude is the distance from rest. So I need to know where rest is, and that's in the middle. So finding the middle between 11 and 21, we can average them. 11 plus 21 divided by 2 would be 32. Divided by 2 is 16. So if I want to find that axis in the middle, I can average them and I will get 16. That will show me that the amplitude is 5 above the 16 and 5 below the 16. The amplitude is 5. You can also find the amplitude by doing highest, subtract lowest, divided by 2 as well, because the amplitude is the distance from rest, not the total range. Phase shift. That's probably the trickiest decision. The phase shift depends on which function we're thinking this would best be represented by, sine or cos. This one to me starts on a low, goes to high, goes back to low again. So it most closely, to my eyes, represents a cos function upside down. So if I'm going to use cos and not sine, then this does not have a phase shift. It's just upside down. If I chose sine as my function, my parent function, then there would be a phase shift. But I'm going to choose cos because it's easiest. And lastly, the displacement. Sorry, coughing away here. The displacement is whether this function has been moved up or down from the normal parent function. And the normal parent function has an axis of rest along the x-axis, or y equals 0. This one has an axis of rest at 16. So it has been moved up 16. We have all the bits and pieces that we need. We just need to determine the equation. So I thought my function looked most closely like a cos function and not a sine. So I'm going to set up my function with some space for all the numbers that I need. First of all, I need to know what the amplitude is, and it's 5. It's also upside down for a cos function. It's starting on a low instead of a maximum. So we're going to write -5. Then I need to write in the b value, which would indicate our period, which would be 30 if I solve for b. In the brackets with x, or t, I guess, time in this one, I would write my phase shift. There isn't a phase shift. So I just need t. And then my displacement is 16. And there I have my equation. For those of you that like a challenge, how would this equation change if you decided to use sine instead of cos? I have a number of questions for you, page 379 and 384, where we're just looking at what the transformations are. And guess what we get to do tomorrow?